Homework solution 4.9. Two generators are connected in parallel to supply a load of 3.25 megawatts at 0.82 power factor lagging. Generator 1 has a no-load frequency of 61.25 Hz and a slope of SP equals 1.1 megawatt per Hz. Generator 2 has a no-load frequency of 61.0 Hz and an SP equal to 1.0 megawatts per Hz. What's the system frequency and what is the power share between the generators? If an additional 800 kilowatts of load is added to the system, what's the new system frequency and what's the new power share between the generators? In part C, the system operator wants to restore the system frequency to that found in part B. What should the no load frequency set point be changed to if generator 1 is used to perform the control? So the givens here are that we've got a load power of 3.25 megawatts. A power factor equals 0.82. Lagging. We've got a no-load frequency FNL. This is for Gen 1, so I'll put a little subscript there to indicate that. FNL1 is equal to 61.25 Hertz. The frequency droop characteristic is 1.1 megawatt per Hertz. The no load or the generator set point of unit 2 is equal to 61.0 Hertz, and the frequency droop characteristic of unit 2 is 1.0 megawatt per Hertz. Find in part A what is the system frequency, what is P1 and what is P2, right? Part B is the new system frequency, the new P1, and the new P2 for P load plus 800 kilowatts. And then in part C, we're asked to adjust generator 1, so we want to know what is the new no load set point to get the system frequency restored. So the solution to this is similar to the last example, but we have to draw two frequency droop characteristic plots back to back. We call this a house diagram. Sorry about that. So we draw them back to back. Again, we call this a house diagram. The y-axis is still frequency. The x-axis now has power from Gen 1 and power from generator 2. This is still the 0 watt point. So they both have slope characteristics. This guy intersected at 61.25 Hertz, and its slope was 1.1 megawatt per Hertz. And then this guy here, just draw it going the other direction, it intersected at 61 Hertz. And the slope of that line was 1.0 megawatt per Hertz. Again, I'm using the term slope loosely. Now, what we're going to do, since they're connected together, they have to have the same electrical frequency. So this is the system frequency, FSys, that they operate at. So we just find that number, find out where this line intersects with this curve. That's the power sourced by P2, and that's the power sourced by P1. There's one additional constraint, is that since there's only two generators and one load here, that P1 plus P2 has to equal the load. So now we've got enough conditions that we can write an equation that's solvable, and that is P load equals P1 plus P2, and that means P load is equal to SP1 times the no load set point of Gen 1 minus the system frequency plus the frequency droop characteristic of Gen 2 times the no load set point of generator 2 minus the system frequency. So we were given this, 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 and this. That just leaves one variable, fsys. So 3.25 megawatts is equal to 1.1 megawatt per hertz times 61.25 minus fsys, which is what we don't know, plus SP2, which was 61.0, sorry, 1.0 times 61.0 minus fsys. So a little more complicated to solve than the last problem, but not too terrible. I think you guys can figure that out. You all can figure that out. That's fsys is going to be equal to 59.5833 hertz. So I've determined my system frequency. Now I can take this and plug them back into these two equations separately to determine the power share between the two. So the power from Gen 1 is going to be 1.1 megawatt per hertz times 61.25 minus 59.5833. That's 1.8333 repeating megawatts. And P2 is going to be equal to 1.0 megawatt per hertz times 61.0 minus 59.5833. So it's set point minus the system frequency, 1.417 megawatts. If we add those together, we see that we get 3.25. There's a little rounding there, but those are the answers: P1, P2, and fsys. So that is part A. Part B asked us what happens if the load increases. I forget by how much. Let's scroll back up there. The load went up 800 kilowatts. Nothing else changed. So we can see that this is just going to be 3.25 megawatts plus 800 kilowatts, which is just 0.8 megawatts, is equal to all this same stuff right here. It hasn't changed the problem format at all. So I get that right there, and doing my solving for system frequency, I see that the frequency is going to go to 59.2024 hertz. So it has decreased a little bit, gone down because of the addition of that load. The P1 is going to be equal to 1.1 megawatt per hertz times 61.25 minus 59.2024 gives me 2.255 megawatt. And P2 is equal to 1.8 megawatt. In part C, we were asked to adjust the no-load set point of Gen 1 to get the system frequency back to 59.5833. And so that's this 4.05 megawatts is equal to 1.1 times no load 1. That's the variable we're changing, the Gen 1 set point. So solving this equation for the no load set point, we get 61.9675 hertz. And if we do that, that will adjust the total system frequency back to this value right here.